This video covers LR and LC circuits. An RL circuit, or an LR circuit, is just a resistor and inductor in series with each other. Now, these rules are going to be very similar for an inductor as they were for a capacitor, but there are very key differences. First off, an uncharged inductor, which means at time is equal to 0, it acts like a break in the circuit. Whereas a charged inductor, meaning that it's been on for a very long time, acts like a wire. Now, for capacitors, this was opposite, so we need to make sure that we can distinguish between the two. So for an RL circuit, while charging, the magnetic field increases from 0 to B. Again, the magnetic field in this case is the magnetic field inside of a solenoid. The current actually goes from 0 to sigma over R. Again, this is equal to current, which comes from V over R. And the voltage across the inductor decreases from negative potential to 0. Now, just like with conductors, we can derive an equation for the current going through an inductor connected to a resistor. So we're going to start off with Kirchhoff's rules, meaning sigma minus our potential across a resistor, which is IR, minus our potential across an inductor, which is L di dt, is equal to 0. So here we don't have to make any substitutions because we already have I and di in our circuit. So here we're going to move L di dt to the other side. You want to get L out of there. So I'm going to divide by L. Here you have a common denominator, so we can leave that in our equation. And just like with capacitors, we want to move dt up and the equation including I down to the bottom. So our function now looks like di over sigma minus IR. So we can do the exact same thing that we did with capacitors. We're going to take the integral of both sides. So on the left-hand side, this simply becomes t, because that is the only thing we're taking the integral with respect to. On this side, u is equal to sigma minus IR. If we take the derivative of that, that's negative I di. This is r di. And then we want to get di by itself, so that's du divided by negative r. So wherever I see a di, I'm going to replace it with du over negative r. So that becomes du 1 over r. And then I still have u down at the bottom. So I'm going to put negative r up to the other side. And I have du over u. And then I can take the integral. Oh, be careful. I can take the integral of this now, which just becomes the ln of u. We said u was sigma minus IR. And we're going to evaluate this integral from our current is equal to 0 to our current is equal to I. So that becomes negative r over LT is equal to the natural log of sigma minus IR over just sigma. The reason for that is if we plug in that 0 back in for I, that becomes 0 and we have sigma left over. To get rid of that natural log, we take the e of both sides. Sigma comes up. And then the whole goal was to get I by itself so that we have a function for I. So I'm going to move this piece over to the other side, and then I'm going to get IR over to the left-hand side. So that becomes IR equals sigma minus sigma E to the negative R over L times T. And then just to clean this up, I can pull sigma out. That becomes 1 minus E to the negative R over L times T. And I have IR on the left-hand side. And then finally, we can get I by itself by dividing by R. So then my final equation is I is equal to sigma over R, 1 minus E to the negative R over L, all of that times T. Now, just like before, you can double check this equation. If I put in T is equal to 0, then this E looks like E to the 0 power, which just gives me 1. So I get current is equal to 0 at the beginning. Again, it makes sense. We said an inductor that is uncharged acts like a break in the circuit, so it actually has 0 current that runs through it. So this is true for an inductor. Then we can look for when this has been on for a very long time. When that's true, this is an infinitely large number, which means that the fraction is an infinitely small number, essentially 0. So 1 minus 0 means that all we're left with is sigma over R, which again, you should recognize as V over R, which is just our maximum current. Essentially, if my inductor were not even there, this is the current that would run through it. So now we're going to look at the time constant. Like we said with capacitors, our time constant was equal to R times C, and this was equal to Greek letter tau. Now we're going to do the same thing for a inductor, but now R over L is not going to equal tau. It's actually going to be L over R, so that we get the same result, but we want it to say T over tau. So that means tau has to be equal to L over R in order for us to get the same result. So just like before, it was negative T over tau. Tau has to be L over R in order for us to get the same result as we see here. So now we're going to look at the discharging function. Again, we can start with Kirchhoff's loop rule. The potential of the battery minus the potential across the resistor minus the potential across the inductor is equal to 0. Here, we no longer have our battery connected, which means we're adding a wire here. So the process is the same. You want to get Di and I on the same side. So if we move IR to the other side, we have negative L Di dt. We can move dt up and L and negative L away from there. And we can move I down to the bottom so that it looks like Di over I is equal to negative R over L dt. Take the integral of both sides. Here, this is going to give us natural log of I. Now, our limits are I naught, so it has to have a current going through it at the beginning, which means that it is charged, to I, meaning that we're going to solve for the current at some time later after it started discharging. On the left-hand side, it's just from 0 to T, so that becomes R over L times T. This is just I over I naught, natural log. And then we can get rid of the natural log by doing our E's. And then we want to get I by itself, so we can multiply by I naught. So our final equation is I as a function of t is equal to I naught e to negative r over L times t. Or, like we saw in our previous section, t over tau, where tau is equal to L over R. And then we'll be graphing all of these in class. And finally, we can look at an LC circuit, which means that we have an inductor and a capacitor both in series. Now here, you're going to want to imagine this as a mass spring system. So what happens is when you have a conductor that's fully charged and an inductor that's not charged, then you're going to have the capacitor start to discharge. But as you discharge the capacitor, the inductor charges up. And then when the capacitor is completely discharged, the inductor is completely charged. Then you're going to see that because the inductor is completely charged, it's going to start to oscillate that current and make it go in the opposite direction. So that means that the capacitor is going to start to recharge again. When that happens, the plate signs are different than it was at the beginning. So here you have the plate signs that are different. Now that the plate signs are different, it's going to start discharging and the whole process starts all over again. So if you had perfect conductors and perfect insulators, capacitors, then you would actually have a system that would go on forever. But we know that we actually have resistance in these wires, so that's not going to happen. So let's start with our capacitor and inductor. We're going to start by writing our Kirchhoff's rules. Here we have no battery, but we still have a drop in potential every time. So our drop in potential over a capacitor is Q over C. Our drop in potential over an inductor is L di dt is equal to 0. Here you have both negatives, so we can just change those to positives by moving them to the other side. And now you're going to see a different relationship that we've talked about so far. Remember that di is just dq over dt. So if I make that replacement here, and this is for I, this equation actually becomes the second derivative of charge with respect to time. Now you have a charge, and you can put them on and do the process very similar. But you're going to notice that if I move this piece to the other side, I get Q over C is equal to negative L, second derivative. And we haven't had a second derivative in these functions before, but we have had these kind of derivatives with simple harmonic motion. So I want to show you that if I move L down to the bottom and I take away that negative, then I have 1 over LC Q equals the second derivative of Q with respect to T. So we said that any time that happens, I can use my equation that in this case Q is equal to Q cosine omega T, where this is Q naught, the original charge. So then our second derivative of that is negative omega squared Q naught cosine omega T. If we make those substitutions in for Q and the second derivative of Q, then you're going to see that this piece and this piece will cancel out. So all you're left with is negative 1 over LC is equal to negative omega squared. The negatives cancel out, and I get omega is equal to the square root of 1 over LC. And remember that that is equal to 2 pi over t. So if I wanted a function for the period, it would just be period is equal to 2 pi times the square root of L times C. So one of the things that's most important is that for this section, it might ask you for the time rate of change. Remember that this is di dt. So if it asks you for the time rate of change of current, then it's asking you for this portion here. So we said that you can think of this as a mass spring system. Well, what was true for a mass spring system is that my total energy was always the sum of my potential plus kinetic. Well, that's true for this situation. My total energy will always be equal to the energy on a capacitor plus the energy on an inductor. Now, when these two are at their maximums, then you can set them equal to each other and this equation will actually help you solve for information that you might be missing.